SwayamPrabha. Digital India. Educated India.
Then our next assumption after autocorrelation, it says this is the assumption of multicollinearity. Multicollinearity. What does it mean? I'll explain with an example. Let's say our model is yi equals to alpha plus beta 1 x1I plus beta 2 x2I plus beta 3 x3I plus beta k xki plus ui. Okay. So basically multicollinearity says that there should not be a high degree of correlation between any two variables. So that means correlation between x1i and x2i or correlation between x1i, x3i or correlation between x1, x2i, x3i. So this type of correlation should be insignificant, very small. If it is high, then we say that there is a presence of multicollinearity. Collinearity means linear, perfect linear relationship, and multi means multiple such perfect linear relationship between x1, x2, that is one relationship, x2, x3, that is another relationship, x2, x3, that is another relationship, or x3, xk, that is another relationship. So that means we have perfect linear relationship, and such number of such relationship is multiple. That is why the name called multicollinearity. For example, let's say when you are thinking of consumption, is a function of alpha plus beta 1 income plus beta 2, let's say this is I plus beta 2 wealth plus ui. So consumption function theory says that the consumption depends not only on income but also on wealth. All right, and it is possible that income and wealth is highly correlated among each other. Income and wealth, they are highly correlated. If that is the case, then we say that this particular data suffers from multicollinearity problem. And in presence of multicollinearity problem, again the three desirable properties of unbiasedness, efficiency and consistency, they may get disturbed. Okay. So these are the assumptions. That we specify before we estimate the model using CLRM in classical linear regression model. So after maintaining this assumption, we need to proceed for estimation, right? We need to proceed for estimation. And now we will try to understand how we estimate a model, what is the technique that we apply to estimate the model. So that means what are those assumptions? Once again we can recap. We say that firstly their model is linear, there should not be any non-linearity in parameters, it might be linear in variable. Then number 2, it says that when you specify the model, then expectation of ui given xi equals to 0 and ui follows a normal distribution. Then number 3, we say that the model what we specify, that should be in the model xi is fixed over repeated sampling. Xi is fixed over repeated sampling. Then assumption number 4, it says that the covariance between xi and ui, that is 0. So xi is strictly exogenous in the model. Then number 5, it says that your model is basically a model is in your model there is no model misspecification, neither due to improper functional form nor due to inclusion of irrelevant variable or exclusion of an irrelevant variable. Then we said number 6, that total number of observations should be much higher than the number of parameters to be estimated. Then number 7, we say that in your model there should be enough variation in your xi and yi. Then number 8, it says that there should not be any autocorrelation. Then number 9, it says there should not be any heteroscedasticity, and number 10, it says there should not be multicollinearity. I think I have made some mistake in counting, probably you can look at, but basically these are the assumptions. In your textbook also you will see there are 10 such assumptions. Okay, I might have made some mistake, that is why my counting is coming 8, but there are actually 10 such assumptions. So once we specify this assumption, then next step is how to estimate the model. So I will try to make you understand about the estimation procedure. Estimation. So with a simple diagram once again. This is xi, this is yi, and this is your line. Let us say this is my PRF, which is given by expectation of yi given xi equals to alpha plus beta xi. Okay, and let us say this is the line, this is your SRF. So that means this is the population regression function which we are trying to infer about, because this true population parameter alpha and beta, they are never known to us. Okay, they are never known to us. So that is why this is the population regression function, but we have estimated this SRF, and this is basically this is yi hat that we have estimated equals to alpha hat plus beta hat xi. Okay. Now let us say for any given value of xi, let us say this is my xi. Okay, this is my xi. What will happen if you draw a line? Then what you will get? This is your yi, and this yi is actually your actual or observed yi. Okay, so this yi indicates the actual yi. Okay, let us say this is y1i, you can write this is x1i, a specific value. So for a specific value of x1i, your observed y is y1i, right? That means, and this is your y1i, let us say this is your yi hat. Okay, this is your yi hat, and this is your yi population regression function. This is your SRF. So this is your yi hat. So this is your ui. This is your ui and this is ui hat. Ui hat. So that means from this relationship what I can write that yi equals to then yi hat plus ui hat. So that means we can write alpha hat plus beta hat xi plus ui hat. This is what you can write, and ui is basically yi minus yi hat is ui. This is the relationship. So that means in this technique we are trying to fit a line which is basically SRF by drawing a particular sample from the population, so that we can infer something about this PRF. And if you draw multiple samples, then you will get multiple such SRF. And our objective is to estimate the SRF in such a way that SRF goes as close as possible towards this PRF. This is what we are trying to estimate. Now, how are you going to do that? How are you going to do that? See, if we specify a line once again, this is xi, this is yi, this is figure 1, let us say this is figure 2, this is xi, this is yi. Okay. So, for any given value of xi, what will happen? You will get your predicted yi like this. Your actual yi would be, let us say this is y1i, but this is your predicted value. So that means you will commit some mistake. Let us say this is u1i, right, when x is x1i. Then for the second one, let us say this is x2i, your predicted is here, but your actual may go here. This is, let us say, y2i. So that means this is u2i. Similarly, for x3i, let us say this is your actual y3i. So that means this is your yi hat. So that means this becomes your u3i hat. This is u1i hat, this is u2i hat, this is u3i hat. Okay. So what we will try to do, we will try to minimize this error. If you minimize this error, if you minimize the sum of these errors, then what will happen? Your SRF will go as close as possible to the PRF. Is this clear? You have estimated a line and then you are trying to predict somebody's consumption given his or her income. Now what happens? When you specify a given level of income, your model says that individual's consumption should be here on the line. Okay? But if you see the actual consumption is lower than this line. That means you are committing a mistake. Let us say that is u1i hat. For x2i, your model predicts the consumption here, but you see your actual consumption is over the line. That means there also you are committing mistake. Let us say that is u2i hat. For the third individual, this is x3i, your actual is here, observed is here, once again you are committing mistake. So that means some errors are positive, some errors are negative, and what is our objective here is to minimize this error. We are trying to minimize this error. Okay? Minimize this error. Now, if you minimize the sum of ui hat, what will happen? What is the value of summation ui hat? What is the value of summation ui hat? Can you think of? Sum of ui hat is actually 0. Why this is so? Because this line, this SRF line, what we have discussed earlier, that this is basically an average line. This is basically an average line. So, this u1 I hat, u2 I hat, u3 I hat, all these errors are basically deviation from the average line. And what is the sum of deviation from the average or mean? Sum of deviation from the average or mean is actually 0. That is why summation ui hat is 0. So, we cannot actually minimize this ui hat. Rather, what we have to do, you have to minimize summation ui hat square. Otherwise, the positive errors will get cancelled out by the negative errors. Okay? So, that means we are trying to minimize this summation ui hat square. And what is summation ui hat square? That is nothing but, that means this implies we are minimizing summation. What is ui hat square? If you look at here, yi equals to alpha hat plus beta hat xi plus ui. So, that means basically you are minimizing yi minus alpha hat minus beta hat xi, that square. And what is your control? You are trying to minimize this with respect to alpha hat and beta hat. Okay. So, if you, how do you minimize? You have to differentiate this function. If you differentiate with respect to alpha, you will get one equation, you have to set it equals to 0. As you all know the rule of minimization or maximization, you have to differentiate again this with respect to beta hat, that again if you minimize this, you will get that means you, let us assume that z is equals to summation yi minus alpha hat minus beta hat xi square. So, basically then minimization required del z del alpha hat equals to 0, del z del beta hat equals to 0. These two, if you write you will get two normal equation. Two normal equations with two unknown alpha hat and beta hat, with two unknown. Right. So, if you do so, then what you will get? You will get your beta hat. If you solve these two equation, then you will get your beta hat equals to summation xi minus x bar yi minus y bar yi bar divided by summation xi minus x bar whole square. This is I running from 1 to n, I running from 1 to n. Okay, this is your beta hat. All right. So, that means, and this particular technique what we have applied here by minimizing sum of ui hat square, this technique is known as ordinary least square method. The technique is known as, this particular technique is known as ordinary least square technique. Or OLS in short, OLS. So, this is actually the meaning of estimation, and this is what we actually do. We minimize sum of ui hat square, sum of ui hat square. Now, couple of things that we need to remember here. That when we minimize this is xi, yi, this is your line, and let us say these are all my error term. Okay, let's say this is u1 hat, this is u2 hat, this is u3 hat, this is u4 hat, this is u5 hat, like that. So when you are minimizing summation ui hat square, it is basically minimizing summation u1 hat square plus u2 hat square plus dot dot u in hat square, ui hat square, right? Now what does it mean? It means I am giving equal weightage. What does it mean? Equal weightage. Equal weightage to all the error terms. Okay, all right. So what is happening? If you square it up, since it is u1 hat square, u2 hat square, u3 hat square, and all these are getting equal weightage. So if you look at from the diagram, some of the points are very close to your estimated line. That is why some predictions are very close towards the point, towards the SRF, and some predictions, some points, some errors are much away from the line. So obviously the lines which are closer to the line should get more weightage, because these are the points they actually contributed more towards constructing this line SRF, and these are the points which contributed less in constructing this point. But when I am minimizing it by taking summation, even though this point is much away from the line, contributed very less, when I am squaring, it is getting more significance, more importance, and u5 hat square basically dominate u1 hat square, u2 hat square, something like this. So while u5 actually should get less weightage, because of our mechanism of OLS, u5 hat square is actually more weightage in this mechanism. So that is some kind of limitation of this ordinary least square method that we have to keep in mind. So what I am saying, in ordinary least square method, all this error square, u1 hat square, predicted error square, u1 hat square, u2 hat square, dot 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 un square, they all are getting equal weightage. Okay, while we should put more importance to the point which are closer to the line and less to the error term which are far away to the line, because those points contributed very less in the construction of the line. Okay, because this line is nothing but a scatter plot, average of your scatter plot. If you plot your xy, you will get a scatter plot like this, and this line SRF is actually the average representation of the scatter plot. And in that scatter plot, the point which are closer towards the line, they should receive more importance. That is why the error term which are less the error, more should be the weightage, and higher the error, less should be the weightage. But here it is happening just the opposite. When I am squaring out, more the weightage, more the error, larger the weightage, the importance they are giving, because all are getting equal weightage, u1 hat square plus u2 hat square. So the limitation of this OLS method we will discuss in detail in a later part of our discussion, when we will discuss about weighted least square method. Okay, so limitation of OLS would be overcome by the weighted least square method, where we see that higher is your larger is the deviation from the line, these errors will receive lower weightage. Anyway, after that, so this equal weightage, this would be, so this implies that the error terms errors which are far away from the line from the SRF gets more importance. Okay, this is the limitation of the OLS method. So this is the limitation of OLS. So putting equal weightage to U1 hat square, U2 hat square and all these things is giving us this type of problem, and we will overcome this using our weighted least square method. So what we have observed so far, that we have learned what is basically the sample regression function, what is the population regression function, what we are estimating. We are estimating alpha hat and beta hat to predict about, to infer something about the true population parameter alpha and beta, and that we are doing using ordinary least square method, where we are just trying to minimize the sum of UI hat square, and that in that process, since we are putting equal weightage, we are committing some mistakes, because the larger the deviation from the SRF, we are giving higher importance, because if we are squaring, so it is getting magnified. Okay, the error which are already larger in their magnitude, after squaring they are getting magnified, which ideally should not be the case. Okay, larger the deviation, more should be lower should be the weightage, and that we will do in our weighted least square method, which we will discuss later. So with this we are closing our discussion today, and what we will do tomorrow, we will discuss something about some important properties of your estimates beta hat, and we will also take one data set and we will see how to use the software, statistical software, to estimate the model. That would become very interesting. Thank you.